All right, probability. What is this? It's literally just figuring out how likely it is for something to occur. So we talked about why this branch of mathematics is so important. In terms of solving issues and problems, for example, those in the environment, if we can figure out how likely it is that we're going to run out of fossil fuels, or how likely it is that we're going to have water shortages because of climate change, what we can do is predict the future of how likely something is to occur, and we can change our behavior today so that those kind of scary things don't happen. But there's a lot more to probability than that. But that's one reason why it's really important that you understand the branch of mathematics called probability. So we rolled some dice today,
6,
and I asked you what was it. I had one person pick a number.
1,
What's the probability that I will roll a 4?
4,
And there is one 4 out of 6 sides, and so a 4 is our favorable outcome. Our 6 is the total possible outcomes. So since there's one favorable outcome, our chances of rolling a 4 on a 6-sided die are 1/6, or 16.6 repeating percent, or 16 2/3%. You can give it as a fraction, a decimal, or a percent. So how many outcomes are there when you roll a die? Well, there are 6 sides, so there are 6. Can I ever roll a 0? Can I ever roll a 7? Well, since there are no zeros on a 6-sided die, there's only the numbers 1, 2, 3, 4, 5, 6, and there are no 7s, it's impossible for me to roll that. So there are 0 favorable outcomes still out of 6, and 0 divided by 6 is 0. So the smallest probability can be is 0.
6,
And if something has a probability
6,
or a likelihood of happening at 0, that means it's impossible. It cannot happen. So probability really means just how likely is it that something will occur. A mathematical way to see it is to understand the possible outcomes when rolling a die. So the possible outcomes is the denominator, and the favorable outcomes is the numerator. So the probability of an outcome is literally just how many favorable outcomes are there over the possible outcomes. So the denominator is the possible outcomes. So again, what's the probability of rolling a 4? It's 1 out of 6. That means that really a 1/6 of the time I should roll a 4. And does that always happen when we just do a few rolls? Well, not really. But if we did a million rolls, we get closer and closer to that 16 2/3%. All right, and then what about the opposite? What's the probability that I'll roll a counting number from 1 to 6? Well, every single number on this die is a counting number
4,
from 1 to 6. So I have
2,
6 favorable outcomes. Out of 6 possible outcomes, 6 divided by 6 is 1. And remember, 1 is the same as 100%. So this means that the smallest probability can be is 0, and that means it's impossible to happen. So the smallest is a 0, and the biggest probability can be is a 1, and that means something is certain to happen. And everything else is a fraction or a percent in between. So remember, as a percent, 0 is 0%, and as a percent, the number 1 is 100%. So there's no such thing in probability as 200%. It can't be bigger than 100%, because your favorable outcomes can't be larger than your possible outcomes. So we played this game. One player was player A, and the other partner was player B. And in this game, you rolled the dice, and you divided A's number by B's number. So if A rolled a 3 and B rolled a 2, you divided 3 by 2, and that's 1.5. You just take the first digit, a 1, and you record it. If A rolled a 6 and B rolled a 2, we did 6 divided by 2, and we recorded a 3. 3 divided by 4 is 7,500, so we recorded the 7. 4 divided by 5 is 8/10, so we record the 8. 6 divided by 1 was a 6, etc. 5 divided by 6, 5 6 is 0.83 repeating, so we recorded the 8. So you just record the first digit after you do the division of A divided by B. Player A was the winner if the first digit of the quotient was a 1, a 2, or a 3. Player B was the winner if the first digit was a 4, 5, 6, 7, 8, or 9. And then I had you make a prediction or a guess. Do they think the game was fair for player A, or was the game fair for player B? Did A and B have the same chance of winning? So all of you recorded your prediction. Then we needed a way to organize your data, so you made a table, because a table is a great way to organize your information. And on your table, you would on each set of rolls, you recorded A's number, B's number, the first digit only of the quotient, and whether A or B won. And you needed room to play 36 times, and that's what we did next. And recording each roll. This is one class's results. So the number of A's, I circled all the numerators. Those are the number of times out of their 36 that player A actually got the point. And then what we did is we added them and we took the mean. So we added 22, 18, 27, and 25 and divided by 4. And for period 4, the mean was 23 rolls out of 36. 23 times player A won the game. For player B, these were the amount of times out of 36 that B got the point. So we added these and divided by 4, and we got a mean of 13. So it obviously seems like player A had a lot more chances of winning than player B. So the next thing that we did is we decided it didn't seem very fair, and we decided to analyze the game. So here's the way that we did that. We made a table, and we said, okay, player A can roll a 1, 2, 3, 4, 5, or 6. Player B can roll a 1, 2, 3, 4, 5, or 6. So we filled this in by dividing A by B and recording the first digit. 1 divided by 1 is 1. 1 divided by 2 is a half, so that's 0.5, so record the 5. 1 divided by 3 is a third, which is 0.3 as a decimal. The first digit is a 3. 1 divided by 4 is 0.25, first digit is a 2. 1 divided by 5 is 2/10, first digit is a 2. And 1 divided by 6 is 0.16666, but the first digit is a 1. So we did the same thing and filled them all in. And then we literally circled all the ways in which player A gets the point. So out of all the possible outcomes, player A had 23 ways to win. Player B only had 13 outcomes that would give player B the point. So clearly it was an unfair game, and it was just kind of interesting that the mathematical probability of player A winning 23 out of 36 happened in our game in period 4. This only happened in period 4, that the mean of period 4's A's happened to match, our experiment matched mathematically what happens when we analyze the game. So that was kind of cool. Okay, then what digit should player A have in order to make the game more fair for both players? So what you had to do then was figure out how could we change the rules? So player A got the point when it was a 1, a 2, or a 3. Oh, let me go back again. Okay, so player A won the game if the first digit was a 1, 2, or 3, and player B won the game in all of these cases. So at first, all of you thought that it was really unfair, and you thought that player B has so many more ways to win. Player B, it's unfair to player A, because player B has twice as many outcomes as player A. But notice once we analyze the game, we find that, oh, there isn't even a 9 on here. So remember, player B gets a point if there's a 9. Well, scratch that, because there is no 9. And there weren't very many 8s. There were 2 of them here, and there was only 1 7. And a 1 and a 2 occurred. Look how many times a 1 occurred. So many more times, because when I'm dividing 3 by itself, or 3 by 2, or 4 by 3, or 4 by itself, or 5 by 3, or 5 by 4, or 5 by itself, all of those have the first digit as 1. So you had to figure out a way to change the rules to make the game more fair. And one group said, take out the 2 and move it to player B and give player A a 7. And if you look at our table and you count the 1s, 2s, and 7s, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oh, I didn't count that right. Excuse me. I think that's what they came up with. Okay, so I think they took out the 3 and said a 1, 2, or 7. I didn't count that right. Let me try that again. 1, 2, or 7. So the 1s, 2s, or 7. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, maybe it wasn't the 2. I'm remembering it wrong. Maybe it was that they took out. This is how we did this. So let me erase the 2, not take that out, and erase the 7. And what they possibly did was said take out the 3, put the 7 here, and take out the 7 and give the 3 here. Let's try that. 1, 2, or 7. We'll make it blue. All right, try again. So 1, 2, 3, 4. Oops, I'm counting the same thing. Sorry. Count 1, 3, or 7. Sorry. Try that again. Oh, I'm doing really well. It's Friday night at 6:08 and I'm tired. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That's what it was. Phew. So if we change the game so that player A wins, if it's a 1, 2, or 7, then player A has 18 out of 36 ways to win the game. 18 out of 36. And since 18 is half of 36, that means player B gets the other 1836. Phew! And now we have a fair game. And then I just asked you, why do you think I wanted you to roll it 36 times? Well, if you look back at our table, mathematically there are 36 possible outcomes. So when you roll it 36 times, we can compare our experimental probability with what happened mathematically. And that's it. Thanks. Have a great weekend.